Okay, so we are going to start our lecture now. Today we are going to finish chapter 8. So that will be the Mary size here. We are going to finish chapter 8 today, and this will be the last chapter for exam 2. So exam 2 covers chapter 5 to 8. And on Monday, we are going to have a review of the homework, so we can have some examples to work with and see how to solve the problems. And we are going to have an exam on Thursday. Okay, so Tuesday we're still going to do the lecture, but on Wednesday we have a break, and then Thursday we are going to have our exam. I will post the exam Wednesday afternoon, so you can have a day and a half to finish the exam. So anyway, we are going to finish chapter 8 today. Chapter 8 is about potential energy and the conservation of energy. We talked a little bit about this in our lab today, so you know what is potential energy. And conservation of energy means that the total kinetic energy plus potential energy is the same in an isolated system. So we are going to take a look at definition of potential energy. We have the definition here. So potential energy, usually we use letter U, and sometimes we use PE, okay? So KE is kinetic, potential energy is PE, but in our textbook, we use U, so we are going to use U in future. So potential energy U is the energy that can be associated with the configuration of a system of objects that exerts forces on one another. So what does this? So this one here is associated with the object in the system. And we have a lot of system. We have Earth, bamboo. They are different system, okay, as long as you have object in it. And here we have different type of potential energy. One very important type is what we call gravitational potential energy, which is what we did in class today. So gravitational potential energy accounts for kinetic energy increase during the fall. And we also have elastic potential energy accounts for the deceleration by the boundary cord. So we have different type of potential energy in we are going to talk about both in our lecture, but gravitational potential energy is being used more often in our class because every object on Earth's surface will have gravitational potential energy. So we have to know how to calculate potential energy, and potential energy, I told you in lab, is the potential to do work. So if you have a bigger potential energy, that means you are going to create more damage, and create more damage, it means that it stored a lot of energy, okay? So here we have, for object being raised or lowered, our change of potential energy equals to negative W. So what does this mean? This here, it's work done by gravitational force. Okay, so the change in gravitational potential energy is the negative of the work done. Okay, so if gravitational force is doing positive work, the change in potential energy is negative. But if gravitational force is doing negative work, then the change in potential energy is positive. And this also applies to a spring system. We can see here. Yeah, we can. I want to show you. I want to show you this. Yeah, I want to show you this first. So as we talked in class today, the gravitational potential energy associated with a particle Earth system depend only on the vertical position y of the particle relative to the reference position y. So here, usually we have to have a reference point that y equals to 0. So if the object is here and the y vertical position is y, and then we will have our potential energy U of, so here, gravitational potential energy U will be equal to mgy, okay? So this is how to calculate gravitational potential energy. Now let's go back. With that, so here, with that in mind, the things before makes more sense. So we have here, U will be equal to mgy. So let's go back. So say here, if we have an object that moves from here, let's see, it moves from here to here, okay? So here we have position 1 to position 2. The work done by the gravitational force W will be equal to, so this is the displacement. Work equals to FD cosine phi, right? Here, this is our gravitational force, mg. So the work done by the gravitational force, we can write it like this. It's mg times the displacement times cosine 180. So if the object is rising, so for a rising object, we are going to have work done by gravitational force will be equal to negative mg d. Okay, so for a rising object, negative mgd. But in the meantime, I want you to think about, because our potential energy equals to mgy, right? So going from here to here, what is the change of potential energy? So at this point, we can have a reference point here. This is y1, and then from here to here, let's say from here to here, this is y2. So the change of potential energy should be equal to mg y2 final position minus initial position mg y1. So what we have is mg y2 minus y1, and you can say y2 minus y1 is the difference here. That is mgd, okay? So you will see the change of potential energy is actually equal to negative work done by the gravitational force, because this is negative mgd, and the negative become positive. So that's why our delta U will be equal to negative WG, okay? So this is for gravitational potential energy. Change of the potential energy will be equal to the negative work done by the gravitational force. And it's the same for spring. The change in spring potential will be equal to the negative work done by the spring force, okay? So we have some key points here, how to measure potential energy. So the system have two or more objects. A force is being acted between a particle and the rest of the system. So you can see here, this is between the tomato and earth, and this is between the spring and this mass m, okay? So you must have two or more objects. And when the configuration changes, the force does work W1, changing kinetic energy to another form. So we have work. Remember, work also equals to the change of kinetic energy. I don't know if you remember that from our previous class. Work equals to the change of kinetic energy. So here, what we have is the gravitational force is doing work, then that's why we will have change of kinetic energy. So force does work W and also change kinetic energy to another form. And when the configuration change is reversed, the force reverses the energy transfer and doing work too. So the kinetic energy of the tomato or block becomes potential energy, then kinetic energy again. So what does this mean? Here it's we have gravitational force that is doing work. So here, if you take a look at the tomato, so take a look at the tomato, okay? So what we have here is we have kinetic energy of the potato. plus the potential energy of the potato. So think about going from this position to the top point here. What you have is you will have V initial here, but at the top, what you will have V equals to 0. So you will have a lot of kinetic energy here, and then so you have K here, you have K equals to 0 here. In the meantime, what is changing is here we have potential energy because it's the lowest point. Potential energy depends on Y. So here, so this one at this point, you are going to have K maximal, but you will have your potential energy that is, you will have your potential energy that is minimal. And at this point, you are going to have your kinetic energy that is 0. You are going to have your potential energy that is maximal. That's because the height increases. So that is what I want to show you here. It's the potential energy converted to kinetic energy and kinetic energy converted to potential energy during the process of going up and also during the process of going down. Okay. This is it. And we also have different type of forces. We have conservative force. We also have non-conservative force. So for conservative force, we have, so the only thing you need to know about the conservative force is gravitational force and spring force. And all the other forces we are going to talk about in our class is non-conservative force. So what is conservative force? Conservative force means the work done only depend on initial and final position. Okay, it does not depend on the path. Okay, so it doesn't matter. So for example, if you have object 1 going to object 2 here, maybe it's going this way, and going that way. No matter what happens, our gravitational force is always going down, and also the work done equals to mgd. So depend on the vertical height. So our work is always equals to mg, and we should do y2, actually negative. We should do negative y2 minus y1. Okay, so in this case, negative y2 minus y1, because it only depends on the final point and the initial point, does not depend on how the object is being moved. So it could move from here to here, or here to here, or maybe this way. As long as you know initial and final position, then it equals to that. So this force here, if the work done only depend on initial position and final position, is what we call conservative force. And also spring force, it's the spring, it only depend on the initial position of the spring and the final position of the spring. It does not depend on the path. So you can do like the object going back and forth, as long as you know where it starts and where it ends, you can calculate the work done by the spring force. Okay. So here, these are the non-conservative force. Work only depend on initial and final positions, and all the other forces we talked about is non-conservative force, like friction, tension, jack force, normal force, and stuff like that. Okay, so all the other forces except spring force and gravitational force. And the kinetic energy of a moving particle is transferred to heat by friction. So friction, if you have a moving object, okay, if friction exists, we know it will stop. So this amount of kinetic energy is consumed by friction, and the kinetic energy of a moving particle, in the end, it will stop, is transferred to heat by friction. So you will have like some heat generated by the contact, so through the contact surface. So you may not observe this kind of heat in your daily life, like normally when you see the motion, but what if you do this? So I'm going to turn on my camera. So friction can create heat. What you do here is we can just rub our hand against each other, okay? So after a little bit, you are going to feel heat is being accumulated among your hand. Why is that? That is because when we do this, we are applying friction along the hands, okay? So friction along the hands, and the friction is doing work because we have relative motion, we have the displacement. So after a long time, friction is doing work, and the work done by friction is being transferred to heat to your hand. So that's why you will feel the warm, okay? So this is an example. And also we have other examples like, yeah, you rub your hand against table, or you rub two objects against each other, and then you touch the surface, you are going to see the temperature of the surface increase. So work done by friction will be transferred to heat, okay? So work done by friction will decrease your kinetic energy, and that kind of energy is transferred to heat. So this is that. And the thermal energy cannot be recovered back into kinetic energy of the object via friction force. So if you have thermal energy, the thermal energy is generated by friction, but cannot transfer back to kinetic energy from friction. So therefore, the force is not conservative. Thermal energy is not a potential energy. But for gravitational potential energy, you can say kinetic energy and potential energy can be transferred from each other, like in the previous picture. See here, you have a lot of kinetic energy. When go to here, you have zero kinetic energy, but maximum potential energy, and then the force back, what will happen is you are going to have smaller potential energy, but bigger kinetic energy. So for conservative force, the energy can be transferred through the forces. Okay. So when only conservative force act on a particle, we can find many problems can be simplified. So the network done by a conservative force on a particle moving around any closed path is zero. So what does this mean? It means if you have an object moved from here and you have a weird path go back to here, the work done by the gravitational force equals to zero because it depends on initial position and final position, but here initial position equals to a final position. So that's why there's no work done by the gravitational force. So see here, you can see it's the same we talked before. The work done by a conservative force on a particle moving between 2 points does not depend on the path taken by the particle, only depend on the initial position and also the final position. Okay. So if the force is conservative, any choice of path between the 2 points A and B gives the same amount of work. And also around the trip. Around the trip means a closed path. You are going to have a total work of zero. I do not really like how this book explains potential energy. I always tell my student it's you virtual the position of the, so you choose a reference point and you try to get the position of the object referred to your reference point, and the bigger the height, the bigger the potential. So this is easier to understand rather than finding out the work done by the gravitational force, rather than using this equation, okay? So using delta U equals to mgy2 minus mgy1, okay? It's the same thing, but this is easier to understand, okay, how the potential energy is changed by changing the position of the object. Okay, and then mathematically we have here it's WAB what is this? This is work done by the gravitational force using path 1 will be equal to using path 2, going from A to B. You see, going from A to B, path 1 and path 2, you have the same amount of work. So you can say here, the gravitational force is conservative, so any choice of the path between the point A to B, or you can choose this curved path, or you can choose this path, you are going to have the same amount of work. And this work equals to the negative change of potential energy. It will be equal to mgyb minus mgya, okay, and then negative. Okay, so final position minus the initial position and get a negative sign, it's the work. Okay. So we can take a look at the checkpoint here. So the figure A to B shows 3 paths connecting point A and point B, okay? So a single force F does the indicated work on a particle moving along the path in the indicated direction. So on the basis of this information, is F conservative? So take a look at that. If F is conservative, actually it's not a conservative, because if you want to have going from A to B, your work AB, no matter what path, so will be the same, okay? So if you label this path 1, this path 2, this path 3, okay? So move from A to B, you are going to have, the first one is 60 joule. But the second one, take a look at this. This is from B to A. B to A is 60 joule, then A to B will be, so WA to B along the second path should be negative 60 joule. And also from A to B in path 3 is 60 joule. Okay, so one is 60, the other one is negative 6. Oh, this is also negative 60. 60, negative 60, and 60. So F is not a conservative, okay? So it gives you different. So say here, if you choose this path, the work going from A, going back to A is actually 120 joules. So the paths from A to B have different signs, 60, negative 60, and negative 60. So that's why F is not a conservative. If you want to have a conservative force, you must have all the work done by different paths is the same sign and same value. Okay? So that is that is conservative force. And we also have this general case, how to calculate your work. This is by integration, work equals to Fx dx, doing integration from initial position to the final position. So the potential energy, delta U, will be equal to negative W. So that's why you have this negative sign here, going from initial position to final position. So using this to calculate the potential energy P relative to a reference configuration, where we choose our reference point equals to 0, then our potential energy is mgy. So this is more important, okay? U equals to mgy, but it's coming from the work done by the gravitational force. Okay, so we know that already. And also here, the same process to calculate the spring potential. Calculate spring potential is also we get change of potential energy will be equal to negative work. And here we are going to have Kx. This is what we call the Hooke's law. We are going to verify Hooke's law in our next lab. So negative Kx dx. And then we are going to have integration, and then we are going to have a negative sign here, negative W. And then you are going to get your change of potential energy will be equal to this, okay? So doing integration, you are going to get this. And then if our initial position reference point is x initial equals to 0 for a relaxed spring, then your potential energy of a spring depends on the stretchment or compression. So see here, think about this. So a compressed spring can do work, right? If you compress a spring, you can see it has potential to do work. So we have those doors that can be opened by the spring. So if the spring is compressed or stretched, it has potential to do work. And you can see the more compression you have, the bigger potential to do work. It's the same as our gravitational potential energy equals to mgh. The higher, we use mgy, okay? The higher the position, the bigger the potential to do work. And also this is the same. This X represents compression or stretchment, okay? So this X here. So the bigger the X, the bigger the compression or stretchment, the bigger the potential. So the higher the potential to do work. So that's why you have 1/2 kx squared. It's being derived from doing the integration, but try to understand it conceptually. It's find the position, and the bigger the position, the higher the position, the bigger the compression or stretchment, the bigger the potential. Okay, so with that being said, let's take a look at this potential or this conceptual example here. A particle is to move along x-axis from x equals to 0 to x1. So you can see here x0 to x1, while a conservative force directed along the x-axis acts on the particle. So you have a force acting on the particle. So the figure shows 3 situations in which x component of the force varies with x. So here you have the force. The force have the same maximal magnitude F1 in all 3 situations. So maximal F1 is here, okay? So rank the situation according to the change in associated potential energy during the particle's motion. Most positive first. So you need to understand this. It's change of potential energy from the definition here. Change of potential energy is negative. The integration here. This integration, what we know about this integration is if you do an integration from calculus, you know, doing integration for a function fx is actually the area under the curve, right? Okay. So integration is the area under the curve. And here we have our f. If you want to see w equals to, so w down by f, then it's the area under the curve. So this guy here is your work, and this guy here is your work, and this guy here is your work. And also delta U here will be equal to negative work done by the force. So which one is the biggest? So see here, this is negative. Negative become positive. So this guy will be positive. This guy here is maximal. And here you have biggest area, but you need to take area. So this guy here is the smallest because it's the negative of this area. So then we have 3, we have 1, and then we have 2. Remember, it's the negative. So rank the negative of the area under the curve. Okay, so f dx is the work, and the work doing integration is the area under the curve. So this is that. So that's why we have 3, 1, 2, positive first. Okay, now we know that, then we have one thing that involves a lot of calculation, it's conservation of mechanical energy, okay? So we talked about the kinetic energy is 1/2 mv squared, that's our K, and our U, we may have two parts. One is mgy, the other one, if you have spring force, is 1/2 kx squared. So this is potential, gravitational potential energy, and this is spring potential energy, okay? So G represents gravitational, S represents spring. So here, these are the kinetic and potential energy we know, and what is conservation of energy. So total mechanical energy have these two parts. One is kinetic, which is 1/2 mv squared, and one is potential. So add these two is our mechanical. So the mechanical energy of a system is the sum of its potential U plus kinetic K energy, okay? Total equals to K plus U. So work done by the conservative force increase K and decrease U by that amount. So delta K equals to negative delta U. And then for an isolated system, we only have conservative force. Then we are going to have K2 plus U2 will be equal to K1 plus U1. Okay, so this is the conservation of energy. Final together will be equal to initial of the K and U together, okay? So conserved means these two can be transferred from one to another, but in the total will be the same, okay? So that's why we have this definition here. What is conservation of energy? It's in an isolated system where only conservative forces cause energy change, so only spring force or gravitational force. The kinetic energy and the potential energy can change, but their sum, the total mechanical energy of the system cannot change. So E equals to K plus U equals to a constant. Okay, so this is the conservation of energy. And then that's the same as delta E equals to delta U plus delta K equals to 0. And this is very powerful to calculate your energy, okay? And this is here. We have a lot of application of this. So we can choose the lowest point in the system to be U equals to 0, and the highest point we are going to have maximal potential energy and minimal kinetic energy, because kinetic energy is transferred to potential energy. And we can take a look at this conceptual example. And we also have a lot of calculation example. Let's finish this first, okay? So conservation of mechanical energy. The figure shows 4 situations, 1, 2, 3, 4. One in which an initially stationary block is dropped, okay, here. And 3 in which the block is allowed to slide down frictionless ramp. So this ramp are frictionless. So only gravitational force is doing work to the system, okay? So rank the situation according to the kinetic energy of the block at point B. Greatest first, and then rank them according to the speed of the block at the point B, greatest first. So here, if you know the distance here is y. For every point B here, we can write it like this. So Ka plus Ua will be equal to Kb plus Ub. Because this is a frictionless ramp, only there's no there is no other forces except the gravitational force is doing work. So this is Ka plus UA equals to Kb plus UB. The energy is conserved. So basically we are going to have at this point it's dropped from 0, stationary, initial speed is 0. So 0 plus mgy will be equal to, if we choose this is y equals to 0, will be equal to 1/2 mvb squared plus 0, right? U here at point B is 0. Then our VB will be equal to square root of 2gy. So the speed here at point B will be the same. So since there are no non-conservative forces, all of the difference in potential energy must go to kinetic energy. So therefore, the VB is the same, and also kinetic energy at point B will be the same. Okay. So this is conservation of energy. This one we do not have to understand reading the potential energy curve. The only thing I want you to know is this. So if you have a potential energy curve that looks like this, so let me see. This is, let me see if there's anything I want to think. Oh, so here for the potential energy curve, the only thing I want to say is usually for an object, we have a turning points. So turning points is if you have an object going up and going down, so like this. And then this point is what we call turning point, right? So at a turning point, our kinetic energy goes to 0 because if it's not going to 0, it will keep going up. If it's not 0, this object will keep going up. So for turning point, you are going to have your kinetic energy equals to 0. And then the turning point is the particle changes direction, okay? And also, at equilibrium points, the slope of U is 0. So equilibrium points means your net force equals to 0. So net force equals to 0, and we are going to have our slope. So there is no change of potential energy. So you can kind of take a look at the picture here. You see these points and these points and these points, the slope is 0, right? Slope is 0. So that is the point where our force is 0. So you can see here, x2, x1, and x4. So x2, wait, not x2, x1, x2, x3, and x4, the forces are 0, okay? And also, you have 0 slope here, and then this is 0. And take a look at this. You have here is slope is 0, here slope is 0, here slope is 0. If you want to draw the, actually, the forces, these are 0. And here you have your total mechanic energy is 5 joules. So this is the constant. And you can find out your kinetic energy. So kinetic energy will be the 5 minus the potential energy, okay? And the difference between the total energy and the potential energy is your kinetic energy. And you can also find out where your kinetic energy goes to 0. So this point is your kinetic energy goes to 0. Do you see? So this point, kinetic energy is 0 because your potential energy is 5. So this will be the turning point, okay? So the particle cannot go farther left because your kinetic energy is 0, so turning point. And also we have here this point, kinetic energy, because your potential energy is 0, so your kinetic energy at this point is the farthest. So the greatest, biggest, so the particle is moving at the fastest rate. You don't have to know how to draw these pictures, but at least I want you to know it's understand. So remember the picture that actually we did in class. It looks like this, this, and this, right? Okay, so this is the picture we get in class. So E here, you can see E represents this straight line. It's a constant. So that's conservation of energy. And your PE looks like this. Your KE looks like this. So at this point, we have maximal potential energy. And at this point, at minimal, we have minimal kinetic energy. Right? Usually our kinetic energy at this point should go to 0, okay? Minimal kinetic energy. And this is where you remember the M1, it is going down first and then going up, right? For your M2. So this is the turning point, which is this point here. So here your M1 is going, your M1 is going down and up, your M2 is going up and going down. So do like this. So this is a turning point, which corresponding to the point here. And this point, you have maximal potential energy. So the pictures that we get in the lab actually shows you how the conversion is between your potential energy and the kinetic energy. So minimal kinetic energy is the turning point, and the maximal potential energy, it's maximal potential energy. So see here, this curve is convert, so here, from here to here and here to here. This is kinetic energy decreasing, but your potential energy increasing. So kinetic energy is transferred to your potential energy. Okay, so understand the curves that we get from lab today. Okay. And you don't need to do this problem. Now we are going to take a look at 8.4. It's work done on a system by external forces. So if we do have forces on the system, then our mechanical energy will change, okay? So see here, we can extend work on an object to work on a system. So work is energy transferred to or from a system by means of external force acting on that system. So for a system of more than one particle, work can change both kinetic energy and potential energy or other forms of energy. So that's why you are going to have work equals to the change of your mechanical energy. So if there's no conservative force, your delta U plus delta K is 0. But if you are doing some input to the system, W is the input, then this is not 0 anymore. It will be equal to the change of the work done on the system, okay? So your lifting force, if you have this bowling ball here, your lifting force transfer energy to kinetic energy and potential energy. So you try to move it up, you are doing work. So you have input work to the system, and then the potential and kinetic energy will change. So the mechanical energy will change too. Okay. And for a system with friction, for friction, you can kind of see we have delta ETH here. This TH means thermal energy. That means the work done by friction all transferred to heat energy, which is thermal energy, okay? So for a system with friction, the thermal energy will be equal to work done by the friction. So increase in thermal energy by sliding. So if you have something that is sliding, then friction doing work, then you will have increase of thermal energy, okay? So W, the work done to the system, will be equal to the change of mechanical energy plus the change of thermal energy, because the energy is being consumed by friction and transferred into thermal energy. The thermal energy comes from the forming and breaking of the wedge between the sliding surfaces. So if you are sliding along surfaces, like repeatedly, you are going to get a smoother and smoother surface. So basically, you are like getting the surface smooth. Okay, so this is that. And the applied force, so here, and take a look at this picture. This is our applied force. Applied force supply energy, so it's doing work F multiplied by D. And the frictional force transfer some of the energy to thermal energy. So the work done by applied force goes into the kinetic energy and also thermal energy. So here W will be equal to the change of E plus change of ETH. Okay, thermal, this is mechanical energy. So work input into the system have two parts, either the mechanical energy or the thermal energy. Okay? And we can take a look at this problem. This is a very good one. How force changes the kinetic energy. So in 3 trials, a block is pushed by a horizontal applied force across a floor that is not frictionless, as shown in this figure, okay? Not frictionless. So the magnitude F of the applied force and the results of pushing on the block speed are given in the table. In all 3 trials, the block is pushed through the same distance d. So rank the 3 trials according to the change in thermal energy of the block and the floor that occurs in that distance d. Greatest first. So here, think about what is thermal energy, because you want to find out the thermal energy, okay? So thermal energy equals to what? Take a look at this. It's because of friction. Thermal energy equals to Fkd. Okay, what is Fk? Fk is friction. It depends on mu k times Fn, right? So no matter what is the applied force, the applied force is horizontal. Will it change normal force in vertical direction? No. So normal force will be the same, and it's the same block, so our surfaces will be the same, our mu k will be the same, coefficient will be the same. So this is the same, D is the same, Fk is the same. So no matter what is happening here and here, the thermal energy part will be the same. So all trials will have the equal thermal energy change. So if the problem, if your homework problem asks you to calculate the change in thermal energy, what you do is you calculate friction multiplied by the distance, okay? So what is the distance? The distance is the distance moved by the object. So that's why in here, Fk is the same, D is the same, so your thermal energy change will also be the same. And then we also have more conservation of energy. This is the same as 8.3, so we can take a look at this. Energy transferred between systems can always be counted for the loss of conservation of energy. So it's the total energy of a system, which include mechanical, thermal, and other internal energy. So total energy, E, so not only mechanical energy, okay, it could have thermal energy and mechanical energy, and also other internal energy, like you may have electric energy and also like chemical energy, so all kinds of energy. So that is the total energy of the system. We only need to calculate these two so far, but you are going to see a lot of different type of energy in future. So the total energy E of a system can change only by amounts of energy that are transferred to or from the system. So you must have something, some input, then you have change. If you do not have any input, nothing will change to the system, okay? So considering only energy transferred through work, so work will be equal to the change of mechanical energy plus the change of thermal plus the change of internal, okay? So total energy, now you have two more terms here, thermal and internal, okay? And here, an isolated system is one for which there can be no external energy transfer. No external energy transfer, then the total energy cannot change. So you are going to have this equation, mechanical change plus thermal change plus internal energy change. Oh, this should be a delta here. Will be equal to 0. So for any given instant, your E1 will be equal to E2 minus these two. Okay, so mechanical energy at point 1 will be equal to mechanical energy at point 2 minus the thermal change minus the internal energy change. Okay, so in an isolated system, we can relate total energy at one instant to another instant. This also tells you that energy cannot be created or destroyed. It can only be transferred from one form to the other, okay? So the total energy of the universe is also a constant. You can only change from one form to the other. So we have this example. Is a very interesting example. Is external force act on a system without doing work. So this is very interesting because see this force here. So the skater pushes herself away from the wall. He turns internal chemical energy in her muscle to kinetic energy. So this force is not doing work. Why is that? Because work has to be equal to F times D times cosine phi. So this force only exists when he was touching the wall. Once he leaves the wall, this force F here will gone. So that's why this force do not have displacement. That's why here, during the push, he's not doing work. The force is doing work. So he turned the internal chemical energy to kinetic energy. So he has speed here. It's not because of this, the work done by the force here is because of the chemical energy transferred to kinetic energy, okay? So her K change is caused by the force from the wall, but the wall does not provide her any energy. So how can I explain this? So there is no input. Yeah, there's no so how do I the wall does not provide her any energy. If you push against the wall, how do you gain internal? How do you gain kinetic energy here? Wait, let's think about it. He pushes the wall and causes of internal chemical energy to kinetic energy. So his muscle is doing work to herself by pushing against the wall. But it's not the wall is doing. Yeah, she pushing against the wall will give her initial speed. And it's easier that we use the impulse momentum theory is F times delta T will be equal to change of momentum, which is M delta V. We will explain this in our next chapter. Okay, it's the force multiplied by the contact time will be equal to the change of momentum. So basically, this process is given this girl some momentum to begin with, then you have initial speed, and that's your kinetic energy. And this part of the kinetic energy is not from the wall, it's from the internal chemical energy of the girl. Okay, and then we have a power. We also know this already. We can expand the definition of power. So in general, power is the rate at which energy is transferred by a force from one type to another. So if we have energy transfer or energy change, so average power will be equal to delta E, so change of energy divided by change in time, okay? And instantaneous power is you taking the time derivative of your change in total energy, okay? So this is chapter 8, okay? So so I do not have our homework. So I don't have my homework in my laptop here, but we are going to have, so try all of your homework today because the due date of our homework is, I think it's the day after tomorrow, and we are going to have all homework worked out on Monday, okay? So we are going to stop chapter 8 here. And I will see everyone on Monday. Okay, so bye-bye. Bye.